Hey there, this is the answer key for the 5.7 through 5.11 quiz on AP Classroom. Okay, all right, so here's question number one. So we have this balanced equation up here and you have this rate law. So we have two mechanisms that are proposed. Mechanism one is right over here, mechanism two is right over there. We want to figure out which of those two are consistent with the rate law. So for a mechanism to be consistent with the rate law, the overall equation has to be the same as what you have in the balanced equation, and the rate law based on the slow step in the mechanism has to match up with what was experimentally determined, which is right there, kx2 to the first order. All right, so looking at mechanism one, first of all, make sure that the overall reaction matches up. So this 2x right here, this would be an intermediate. This would cancel out, so those 2x, and there's 2 x's on the reactant side, so they would cancel. Same thing with this xy2, so those would cancel. So you have x2 and y2 as the two reactants that are left over, and this x2, y2 as the one product, which matches up. And then the rate law for the mechanism is based on the reactant and the slow step. So it's x2, and there's just one of them, so it's going to be x2 to the first order, which matches up. So mechanism one is consistent. Now we check mechanism two, and when we put all these together, again, the two x's will cancel out. The xy is another intermediate, that will cancel out. Y is another intermediate, that cancels out. And this x2y is another intermediate, so that cancels out. So all that's left over is what we have for the original equation. So that works. And then the slow step, we just have x2 as the reactant in the slow step, so it's going to be x2 to the first order, which matches up. So that means letter C, both mechanisms are consistent with the rate law. Okay, so we go to question 2. So the energy diagram for the reaction x plus y equals z is shown above. The addition of a catalyst to this reaction would cause a change in which of the indicated energy differences. So a catalyst is going to give us a lower energy pathway. So it's going to lower this hill right here. So it'll be something like down here. It'll be a lower energy pathway, lower activation energy to get from reactant to product. So that means anything that's measuring to the top of that hill will change. So that's going to be this measurement 1 and measurement 2. The difference between reactant and product, that the catalyst doesn't change that. So it's going to be 1 and 2. So letter D. Okay, so we have question 3. This is another mechanism, but it's showing it in symbol form. So the darker circles, those are representing oxygen atoms. And then this white circle, that's representing a chlorine atom. So the particle model shown above represents a proposed two-step mechanism for the destruction of ozone in the upper atmosphere. All right, so based on the models, which of the following represents a species that acts as a catalyst? So a catalyst is something that's going to show up as a reactant first and a product later. So that's going to be this one circle right here, so a single chlorine atom. So we can go down here. So this is a reactant first and a product later, and it ends up canceling out in the overall equation. So we can go down to our choices. That's going to be letter C, just the single chlorine atom. Question number 4, same two-step mechanism with symbols, but now the question is, based on the proposed mechanism, what is the balanced chemical equation? All right, so we want to cancel out any catalyst and intermediates, so this single chlorine atom will cancel, and this combination of those two different atoms will cancel. That's an intermediate. It's a product first and a reactant later, so that's an intermediate, so that cancels. So what's left over is 2 of these O3 or ozone molecules, and then 3 of these O2 molecules. Everything else cancels, so that's going to be letter D. Number 5, another mechanism. So based on the information, which of the following is the initial rate law for the reaction? So we want to look at the reactants in the slow step. So this NOBr2 and NO are the two reactants. But NOBr2 is an intermediate. So we can't have intermediates in the rate law. So we have to go back to step one and see, well, what are the reactants that turn into that intermediate? And we're going to substitute those in. So we substitute in another NO. So it's going to be NO to the second order when we combine those, and Br2 to the first order. So that's going to be letter B. Okay, question 6. We have number of molecules versus molecular energy. So this is a Maxwell-Boltzmann distribution of the energy of the particles. So it's looking for the energy distribution profile, that's curve C, for the Y2 molecules is shown in the graph above for the reaction X plus Y2 yields XY2 when it's done under certain experimental conditions. So line A represents the most probable energy of Y2 molecules. So that's going to be this dashed line right here. That shows the highest point. So that's the highest probability. And line B represents the activation energy. So that's this line right here. So these particles right here, this part of curve C, these particles have enough energy to overcome the activation energy and turn into products. Okay. So the question now is, which of the following changes should be made to the graph to explain the increase in the rate of reaction if the only change in experimental conditions is the addition of a catalyst? So a catalyst works by lowering the activation energy, so you then have more collisions that are effective and can turn into products. So it's going to take this line B, this is represents your activation energy, and it's going to shift it somewhere to the left where it's a lower energy. So line B would be shifted left. So it's letter B. Line B will move to the left because a larger fraction of Y2 molecules will have the minimum energy to overcome the activation energy barrier. So that's the correct answer. Question number 7, another mechanism question. So a reaction mechanism for the destruction of ozone is represented above. In the overall reaction, NO is best described as, well, here's NO. So it shows up as a reactant first and a product later. That's what a catalyst looks like in a mechanism. A catalyst is a reactant first and a product in a later step. So letter B. So this is a 3-step mechanism. So the proposed steps for the catalyzed reaction between this Ce positive 4 and Tl positive 1 are represented above. The products of the overall catalyzed reaction are, so we want to see what's going to cancel out here. So this manganese positive 4 will cancel. This Ce positive 3, that will not cancel, so that's going to be one of our products. Manganese positive 3 will cancel, so that's going to be gone. And manganese positive 2, there's nothing on the, oh, here's a manganese positive 2, so that'll cancel. So all those manganese ions will end up canceling. So then it's just this Tl positive 3, which doesn't show up on the reactant side. So it's going to be the Ce positive 3 and Tl positive 3. So letter B. Okay, so we have this mechanism above, a 3-step mechanism. So which of the following rate laws is consistent with the mechanism? So we want to look at the slow step. So we have one reactant in the slow step, but this again is an intermediate, and intermediates need to be replaced with the reactants that turn into that intermediate. So then we have to replace this NO2F2 with these two reactants right here from the previous step. So it's going to be NO2 to the first order and F2 to the first order. So that's going to be letter A is the correct answer there. All right, question 10, another 3-step mechanism. So which of the following rate laws is consistent with the proposed mechanism? So with this one, we have the slow step as the first step. Now with this, we don't have to worry about intermediates because there's no intermediates in that first step to cancel out on the reactant side. A catalyst, if it does show up, can be in the rate law. So with this, with the slow step being the first step, we just look at the two reactants right here. So HBr to the first order, O2 to the first order. So that's going to be letter B. Okay, another energy pathway. Okay, So we have this energy pathway representing that reaction. So we have path 1 with the higher activation energy, and you have path 2 with the lower activation energy. So the question is, which of the following most likely account for the difference between reaction path 1 and reaction path 2? So when you have a lower energy pathway, that's caused by a catalyst. So it's just lower activation energy. So that means path 2 is a catalyzed reaction. So now we can look down here. So letter D, the presence of a catalyst in path 2. Letter D. Okay, and then the last one, question 12. The role of a catalyst in a chemical reaction is that's just going to lower the activation energy. So that's going to be letter B. It lowers the activation energy, so there's more effective collisions and the reaction goes faster. So letter B is the answer there. All right, and that's it. Have a good day.